Good afternoon, everybody. Julian, can you hear me or can you see me?
Yes, I can hear you. I can see you.
Okay, let me just share my screen. Do you see the presentation?
Yes.
And okay, do you see it?
Looks good. We have 21 attendees. So if you want to wait one more minute, it
Sure.
should be.
Yes, I can wait even more minutes. So maybe you can let me know when I should start and give a short presentation on the PASS conference.
Okay, no problem. I think we have enough participants. Also, Simon joined as well. So I think you can start.
Very good. So welcome back, everybody. Before we start with the presentation or continue the presentation from Simon on deep learning, we want to give you some announcements and also some insight about a conference that we are organizing since a couple of years in Switzerland. This conference is part of a long-term research initiative in Switzerland on scientific computing, high-performance computing in general with applications, and this is called PASC. PASC is the platform for advanced scientific computing, which is about a 10 years research initiative. And as part of this, there's always an annual conference. So far, next year, the conference is in Geneva, 2021. And I would like to kindly invite you to participate in the program, and you can either participate using proposing a mini symposium or paper track. And there's also a poster track available, which I find very much attractive for master students and PhD students in general. So in this case, if you are proposing a poster, you have the chance for a 2-minute presentation in front of the audience. And afterwards, there's always a very nice poster session at the end of the second day where you can introduce your research and also make new friends, colleagues, and also showing your research that you're doing in this area. So the entire program is organized around 8 scientific domains. So this comes from chemistry, material science, life sciences, up to climate and weather is always very important. Computer science and applied mathematics is also important over there. And so we are trying to basically bridge the gap between all these domains and promote computational science and high-performance computing in general in these areas. So the conference chairs next year are 2 colleagues from Dublin and Geneva, and Cindy Ryan and Bastian Chopin. And they are basically in charge of shaping the program around the conference. Here's the program, just to give you an idea about, so we typically have 50 mini symposia. We have a paper track, which is also attractive for computational scientists who want to present a paper. I already mentioned the poster session to you because this is mainly of interest also for master students and PhD students. We have a panel discussion, new challenges and new computing paradigms, which is part of the conference, an interdisciplinary dialogue between experts in 2 different domains, and always social events around the entire conference. Keynotes are next year on quantum computing, which might be of interest for some of you, or I think it could be very attractive. And also a keynote talk from somebody from Technical University of Dresden on domain-specific languages for emerging computer architectures. There's a public lecture which is open to the general public as well. And this is next year about promoting and talking about machine learning, big data, and exascale computing for biodiversity applications from Dalia Conde. So I guess it's a very rich program. The conference is for 4 days in Geneva next year. And if you would like to participate, you might have a look at the PASC conference. You can see the link on this webpage. Or you might ask Tatiana to include you into the newsletter submission, so then you're always up to date about upcoming deadlines for the paper track, poster sessions, and the mini symposium. Yes, maybe this is also one reason why we are showing this to you. I would like to draw your attention to a student participation program, which we have at the conference. And over the last years, we always had quite a larger group of students who were helping us in running the event. The advantage for you is you will probably meet almost all computational scientists in Switzerland, not only in Switzerland, but also in Switzerland, who are working in this research area, but we have also a lot of international participants. You could be part of a team of students within the volunteer program who are helping us in running the entire conference. And just to give you an idea about, I guess this was a picture which we have taken 2 years ago at ETH Zurich. And so these are all master and PhD students from all over the world who were selected in running the program. And what I have heard so far in my experience was that all these students very much enjoyed the participation. So, and it would be very nice if next year some of you will also show up and we could meet in person, hopefully, at the PASC 21 conference in Geneva. So thank you for your attention, and maybe if there are any questions, somebody can inform me. Julian, is there any questions so far? If not, then I would suggest that we continue with the deep learning part from Simon.
Okay, thank you, Olaf. I don't see any questions so far, but you can also write later if you have questions or contact Tatiana. Thanks for that. I think this is really relevant for the audience here. And if you don't mind, I will share the slides on the GitHub repository. So that
exactly. Thank you very much for sharing the slides, and yeah, also for giving me the opportunity to talk about the conference and to promote this to our students as well.
Okay, thank you, Olaf. So let's move to Simon. Back to Simon.
Hello back. Hope you had a good lunch, and let me also add to what Olaf just said. Like, PASC is a really cool conference series, so it's always very pleasant to be there and listen to all sorts of different talks. So if you can attend, I strongly recommend that. So let me go back to the slides. So let me just get back to where we left. So this morning I swamped you with a lot of information about deep learning, or essentially what neural nets are. So flexible function approximators. We learned, you have input nodes, you have hidden layers, you have output nodes. We learned that we need, to train a neural network, we need to first define the architecture. We have cost functions, we have weights, and now we really want to essentially see, numerically what's going on, when we do this optimization of finding the optimal parameters of a network. And for this reason, there is in the next a little less than 2 hours, we will go over those two notebooks. So I will quickly go with them, over with you. And then thereafter, I leave you 10, 15 minutes to play with. The first notebook will be on gradient descent, as we will see in a moment. And then the second one will be an explicit implementation of a neural net with NumPy. So, okay, the first notebook that we will look at in a moment essentially will tell you, again, to repeat myself, so we look for optimal parameters, to be the argmax of some cost function given data. For this, I now invite you to, let me switch to the actual notebook. So it's this one. So you should see it in the materials, but let me actually open it here. So I tested it. So for simplicity, I'm running it here on my laptop, but like on the Jupyter hub of CSCS, this runs smoothly. So I had had few typos that I corrected before. So if you pull right now the repository or update it, you will get the most recent version. So what is this notebook about? So like what we load in first is like, as usual, the plotting libraries, NumPy, blah, 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 blah. SciPy is a library that also contains some optimization routines, but doesn't matter at this moment. So let's just quickly go over it and get an intuition, how we can, find optimal parameters, or like find minima or functions, so to speak. So if you remember, to take, to find the minimum of a function, what we do is we start somewhere in the domain of interest, then we compute the gradient, then we take a little step downhill, and we proceed that until the function doesn't change anymore, or the weights do not change anymore, depending on the formulation. So here is essentially the formulation. Now, what we want to do is to start out with is just something very simple that we can inspect graphically. So we have a function, a polynomial, so search power of x minus 2x squared plus 2. If we plot that thing, if we plot that thing, it looks like this. So we see, between 1 and 2, by eyeballing, we see here is a local optimum, right? So in particular, local minimum. Now, if we want now to do what we learned this morning, like brute force gradient descent, what we need to do is we need to specify, the gradient in the domain of interest. We need obviously to start somewhere in the domain. So we need to choose a starting point, and we need to choose a step size and the criterion, so some norm when we want to stop the iteration. This is exactly what you can see here. So we start at the point 2. So we will start with our computation up here. We will stop the procedure when the precision is 10 to the negative 4 is reached. Step size is 0.1 in the directions. And now, luckily enough, we know, because it's an analytical function, we know the gradient. So f prime, we know it's easy, but for illustrative purposes, it's fine. Now, so we have essentially everything that is needed to do gradient descent. So we do while the absolute value of old minus the new value is larger than some precision that we set here. We do exactly the procedure as stated here in the algorithm. So we compute gradient, we move the function a little bit, and we see what is the difference. So we run that. So with this step size, it took 17 steps to get there. Now let's look at the example. So you can essentially see what's going on. So when we plot the individual steps, it goes down, 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 down until it reaches here. Now, obviously, when you change the step size to say 0, 0, 1, it takes much more iterations because, like it's way more cautious. But every, 0.1 of the step size, it needs to recompute the gradient. So like in that sense, it's conservative. You're unlikely to miss an optimum, a local optimum, but on the other hand side, it becomes computationally more costly. But you see, the basic gradient descent is very easy to do. Now, the thing is, step size is not a good thing to keep constant. So like you may want to do, a step size that is adaptive. So like here, I'm not going into the detail, but the step size in SciPy has a function to determine an optimal step size. So here we reach the same optimum with only 4 steps, but at the same time, computing the optimal step size here comes at a particular cost. So as I said, like tomorrow you will see in TensorFlow, there is plenty of ways for the optimizers to do that. We don't bother too much at this point. What I rather want to insist here is something like more hand waving, which like can trivially implement and experiment with a little bit. Is so for instance, you could say at the beginning you want to take big step sizes, and then you incrementally make it smaller. So like with the notion, okay, at the beginning, you start at an arbitrary point in your domain. You may want to take big steps because like you may be very wrong at the beginning. And then after time, you become more accurate and accurate. So you may want to reduce that thing. So like you see here, choose an initial, arbitrary, not arbitrary, but like pulled out of thin air step size. Then you see with this very trivial update rule that doesn't take a lot of computational resources, you reach the minimum for the same accuracy with only 6 step sizes. So like this is just like to foster a bit of the intuition that you can with this simple algorithm. I mean the plain vanilla algorithm is pretty simple. You can reach an optimum pretty quickly without a lot of coding. Now, that's just, that was baby data, right? So let's, in the next step, try to do something more realistic. Not with neural net yet, but let's do something which introduces 2 complications. Complication 1 is we have data, and complication 2 is we have a model. And what do I mean by that? So the data is here. It's actually pretty funny data set. It chirps, of the little. So like it's the sound of chirping as a function of temperature. So like we have this cloud, And the model that we want to estimate is we want to do a linear regression. So we, like you could, by eyeballing, you could assume, like fitting a line through those points is not a bad thing. So what we need to do right now is obviously to get the optimal parameters we learned before we have the cost function, right? So we do, here we do no mini batch, we take all the data, it's very few data. We write down the cost function with the mean square error. We have the gradient. And then, the rest is as we had it, right? So let's just run those. Now my notebook sleeps. So it's not that computationally intensive. If it would. Hello? So that's a typical thing, like I learned from life, you should never do real-time programming. It's the same, you should never do real.
It might be okay, Simon. For me, it took a few seconds as well on input stamps.
Sorry?
It might be okay.
I don't know. Okay, now we're good. Okay, yeah, okay.
It also took a little bit of time on Dane.
Okay. So you see now it gets the optimal values. So the first parameter is 25 and the third one is 3. And it took, given the parameterization that we have here, like precision and step size, it took, well, okay, half a million, which seems too much. It took quite a few steps to converge. But I mean, you get the notion, right? So you have real data. You need to have a gradient. You take the steps, and then you fit a model to the data. Now let's move on. So I mean, okay, blah blah blah. We can do some plotting as well. So that's all good. So that's the basic. That's the basic gradient descent that you would do for any optimization problem. And now, as I like mentioned this morning, the key for neural nets to be successful is like if you have a lot of data, you cannot just like take a full batch of data. You need to do stochastic gradient descent. So meaning instead of running like here the sum from 1 to a big number, you just take batches of those which are randomized, and you repeat that game until convergence. So for that reason, what I have set up here is way simpler. It's an analytical. So what we do is we have an analytical function, and what we do is we generate 500 sample points around the line 4x plus 10 plus some noise. That's here. So that's it. And what we want to do is we want to find the optimal parameters of this line. So that means we want to find the slope and the offset. So it should be 4 and 10. So what you do typically, and this is then also what we do later on with, in particular tomorrow when you do training of neural nets. So we take the data set and we shuffle it. And now what we do is we take batches of 10,000. The rest remains the same. So let me run this one. So this will indeed now take a little while. But this is what you will see in the end of the day. So what you should see is the cost function. So we have a mean square error, so the cost will go down and then start to to oscillate around and will not go substantially down, because like we have a relatively simple code here. So it's how this will look like. But okay, this will run now a little while. But long story short, what I propose once it's run, what I propose now is to the students right now is we take now roughly 10 minutes where you can essentially experiment a little bit with this notebook to get a little feeling how this gradient descent and stochastic gradient descent is. So what I would propose is, like, what you can do is you can slightly modify this analytical function. You should play a little bit with the starting value, like to see if we start here or here, what will happen. In terms of also like if you modify the step size, how you will converge. Will you always go down, or will you wander around? Okay, see now it's finished. So just like let me jump here. So you see with the stochastic gradient descent, so like we got from we got 10, so 9.98 and 3.9, which is roughly the 2 parameters we would like to. Yeah, so that's pretty much it. So like you have the different knots and bolts to play with. So I would say spend like, well, now we have 2. Let's play 10 minutes with this sheet, and then we get back to the multi-layer perceptron. Just really be brave and play a little bit with it, while I will go on Slack and see if there's questions, and otherwise we will resume with the next spreadsheet, respectively with the lecture at 2:10, if this is okay. And I will, as I said, like I will take questions on Slack in the meantime. So yeah. If I can. So I'm slowly coming back. Dear Radim, could you quickly do a poll to see if everyone is asleep? Yeah, we should get above 30, otherwise we need to send a ring signal.
It seems people are waking up.
Yeah, 26, so let's hope above 13 they continue. One more, come on. Yeah, now we have it. Good, good, good. Okay, so that was just like a first little exercise. Getting a hand feeling again. Like as I said today, it's really to get the intuition for the like the mechanics that is underneath neural nets. So to move on now is what we do now is we want to look at the Python code, a simple Python code for a multi-layer perceptron with a hidden layer. And we want to tackle with that the very basic, the basic problems. So the XOR data set. So I mentioned to you at the very beginning, there was this data set that perceptrons without hidden layers couldn't handle. It's a very classical problem. And, to do so, what we do is now we first look at the basic perceptron code implemented with NumPy. Then we look at a multi-layer perceptron, and then we apply it to very classical data sets and analytical functions. So to start out with, I talked at the very beginning about the perceptron. And the perceptron, the training is very trivial, in fact. So what we have is, so we set the weights, as I mentioned earlier, to some weights, some random numbers, positive random numbers. And then what you have is here again, like the output y, which is is essentially above a threshold, it's 1, otherwise it's 0. And when you do here the update with gradient descent, so that's the basic perceptron implementation, which is like the under the hood of the neural nets. So what you do is, as we will see in the code, we'll first, like go through the data, which will be 4 points. Then we loop over the neurons, compute the activations, and then we're done. The weights, they're updated, as you have seen, just like by NumPy dot product. This can be done very simply. Let me actually show you this one here. So if you open the notebook O2, it consists of 7 parts. So it consists of like a multi-layer perceptron class, and then after, so a perceptron, and then afterwards we will go to multi-layer perceptron and a bunch of test cases. And here, the test case for the perceptron will be 3. So let's quickly step to 3. So this is what I just showed you. So the perceptron, it's a class, we have inputs and targets. we set the the input size. Here's the training. And then one thing which I haven't mentioned that we'll do in a moment. At the end of the day, you know, like in particular for classification, the question is like, what is a measure of success? And for this, one typically starts out with the confusion matrix, which tells, you know, like how, you know, if you have true positive, false negative, etc. Then the data set that you want to look at is the following data set and this one. So what you see, you know, that's the input. So 0, 0, 0, 1, 1, 0, 0, 1, 1, 1. So this is like the 4 points. Then you have 1 point at the lower edge is 0. Then you have 3 you know, ones, class 1. Then we train, so we can do the classification. Well, it's not much more to tell. So this is the basic perceptron to study. Now let me go back to the actual multi-layer perceptron, so the neural net. So the neural net, the code that that you will see in a moment is a bit more intricate, right? So it looks essentially, again, we will initialize the weights. Then for the training, we'll have a forward phase. So that means we need to compute for each neuron in the hidden layer this expression. So like that's essentially W times X. Then we need to do an activation. So here in this code, it will be a particular activation, but like in the implementation, you will see there will be linear, there will be, so linear for regressions, there will be sigmoid, and then there will be tangent with polycus. So we need to do in the forward phase, you know, Wx times sigma for the hidden layer, or hidden layers if there's multiple hidden layers, and for the output. And then we do the backpropagation. We need to compute the gradients to update the weights. And we need to do that for the, you know, essentially we have two weights, right? So essentially we have something like this. So we have one hidden layer. So we have a weight matrix here. We have a weight matrix here. And we need to update those weights in the backward phase. Yeah, so this is what we will look in a moment. So I forgot to show, so this is the data set that we were just running before. But before we look at the code, I just wanted to mention a bunch of you know, remarks again. So the thing is really when you want to, you know, when you do machine learning, what should you worry about? And one thing which is probably sounds ridiculous is the input and the output for your problems. That means you should care about clean data. You should care about, you know, normalization for the data. This is, you know, all common sense thing, but it's important to do so in a first step. So like this is what they're right here, like normalization of the data, that helps you a lot. And then what you also should do is you really have to split the data in training, testing, and validation sets. So like to avoid the overfitting, to remind you to what we have discussed earlier. This is really in particular, I mean, at least training and testing. Then the next thing is again, like it sounds very boring, but I'm repeating myself, the choice of the architecture. That means like how many hidden layers, what is the activations. This is not ex ante clear. So like you need to be, very, well, very
What is the
careful about.
difference between test and validation set?
Yeah, so this is so like, if you forget about neural net for a moment, but like assume you have, say you have two machine learning models. Say you have a simple regression and you have a neural net, for instance. Now you have one data set and you want to apply different models to your data, and you want to essentially have, the best possible model to fit your data. So what you do is you mechanically split the data in 3 chunks. So the first one is to train your model. That's the training set. So you train, say, your regression and your neural net on that one. And then with the next set, so the validation set, you essentially have a way to check the performance. What is the best, the best, best of the 2 models to choose from. And then once you decide which model you want to use, then you use the last chunk of data to actually measure the performance. So now coming back to just neural nets is the following sense. Say if you have 3 different architectures of your network and you want to validate which is you want to figure out the best, what is the best architecture, so to speak. So you run probably the same neural net with 3 different architectures. So like you use the first batch of data to train your models. Then the second chunk of data you use to pick which model, or network architecture you want to choose from. And then the last chunk of data is actually the one you're using to reporting the results, so to speak. That's the mechanically what you do. Yeah, so and then you're on your own. So like this is all like common like mechanical things to do. Once you have chosen normalized your data, you have chosen your architecture, you start to train your network. You have to do your testing, and hope that you don't overfit. Now, before we look at the code, so this has one hidden layer here. So like what you will see is essentially, like 2 blocks in the algorithm, right? So like you need to compute in the backpropagation. So like once we define the error, so we define the activation functions, we measure the gradient, or we compute the gradients for the weights that are from the output layer to the hidden layer, and then from the hidden layer to the input nodes. Then we do the respective updates. Now what I just wanted to mention before, which I forgot and I should have said earlier, so apologies for that. For regressions, being successful is mechanically pretty clear. And what do I mean by that? So like, we have the mean square error of something like, 1 over m. So, like that is easy way to test. But for if you do classification, like the question is what is a measure of success? Obviously, the starting point. So there's a lot of metrics which I'm not going into detail here, but like the easiest way to start out with is the confusion matrix. The confusion matrix essentially, say if you have two classes, and I mean it generalizes for multiple classes. For two classes, you know, you have here no and yes for two classes. Then you have the prediction. Then you have here the true negative ones. You have true positive ones, false negative, and false positive. So you see essentially whenever you know prediction in the test set works or doesn't work. Yes, so there was plenty of chit chat. So what we will do now is let me actually go through the steps through all the slides, and then we go one by one through the examples, and then you know the rest of the afternoon you can play with it on your own. So what we will look at in a moment is, as I mentioned, the XOR data set, which is with the pure perceptron, you cannot deal with that problem, but with the multi-layer perceptron, you can. And here, because you have classification, obviously, we will need to have activation functions that go from 0 to 1 because we have a binary decision, it's a classification. On the other hand side, what we will need for what we need for regression is something which is continuous. So for this, we will have linear activation functions. So what you will see in the code is the following to choose from. So we will have an option linear, that's for regression. And then we have logistic and softmax for the classification. So they do roughly the same thing. What else do I need to mention? Yes, so and then what we look at, we will go together through this multi-layer perceptron code. Then we will run first this XOR data set. Then we will look at the regression where we run, so we essentially approximate an analytical function. Then the third thing that we will do is we will look at a very classical test case, which is the iris data set. So the iris data set, so I'm not, really not a biologist. Is there actually biologists in the audience? Is there?
We can make a short poll.
Sorry?
We can make a short poll.
Ah, yes, please do. No biologist? So I'm not running into danger of making a fool of myself? Or is just everyone very shy? Probably, I don't know.
No, seems like you can go on.
Ah, there is one. There is one.
No, I think it was only Tim to
Ah, okay. Okay. So this is classic. We will look at this data set. It's essentially you have three types or three classes of this iris. So it's iris versicolor, iris setosa, and iris virginica. And they have, so you have the petal and the sepal width or length. So that's the length and the width, whatever. It's like the, so like these are nonlinear decision boundaries. So we should find those. The second one, and then the third one is what I showed you earlier today. This famous data set of Jan LeCun, so the MNEST database of 60,000 handwritten digits. So you can download it from here. And then we will do a classification with that one. So it's again like it's the hello world of machine learning, if you will. And you will see in a moment the code that we will go over is it's really simple to understand, I would say, but still it's powerful enough that it can cope relatively well, at least with this data set. So that's kind of the plan. So let's jump into this. So now let me actually bump up the size a little bit. It should be, so like someone asked, so it's better to read right now, I hope. So that's the basic perceptron class, right? So you have again like specified inputs, the targets. So number of hidden nodes, so like the neurons. And then we have the activation function. So forget about the momentum for a moment. So what we have here in stochastic gradient, it's also like, it's not a plain vanilla a stochastic gradient, but it has a little bit of momentum. So you could imagine just like converges most of the time quicker to the optimum, but it doesn't matter. Conceptually it's the same. So like we specify here the input, the output, and the hidden layer, like the neurons in the hidden layer. Then since you have one hidden layer, so we have, if you have here the layer, you have two weight matrices that we initialize somehow randomly. Then we have this function early stopping. So remember what I mentioned. So we need to split the data into training and test targets. And what it will do is essentially if the error in the test set doesn't decay and we call early stopping, it will stop early. Then the training algorithm itself is the following, right? So you have the inputs. Now here the iteration starts. So one note I didn't say before. So just for simplicity here, we don't do stochastic gradient descent. So it's just a full batch gradient descent, but like everything is simple enough here. So we have, the output. So like we look at this function in a moment. So like we have the forward propagation of the inputs. Here we specify the error. Then we pick the activation functions. So like we have the linear activation function if you want to do regression. We have logistic or softmax, just everything hard-coded. And as I said, like I will leave you alone afterwards the rest of the afternoon to just carefully look at this code. Is self-explanatory. Then here it's about update of the weights. So that's the update of the weight. So like it's the stochastic gradient, so the gradient descent, so the back propagation, right? So we have here the update of the weight matrix 1. Here we have the update of the weight matrix 2. And what is saying here, so like since we use everything, it doesn't matter, but like if you would use a batch gradient descent, you would also need to, randomize the data. Here for the forward function, it's as usual. So like we have the weights multiplied by x. Then again, the different activation functions to choose from. And that's all. And then here we define the confusion matrix. So like you see, that's all, I mean, assuming you know the gradient of your activation functions, which we do, and they're hard-coded. This is a small code, and it's, straightforward to understand, but this is what neural nets can do. Not can do. They look under the hood, roughly. So now let's look at the bunch of examples. So this is the famous XOR data set that I mentioned earlier. So like what we do is we initialize the data set. We specify, actually that's the second example. So we specify here the input data, the output data, and we run it. And you see the confusion matrix. So what we plot here is first of all like the error. The error goes down. But what is more relevant at the end of the day here, like we got this data set right. And as I mentioned at the beginning today, this was a breakthrough. So like the ordinary perceptron wouldn't be able to do that. So that's already quite a success. Now, let's move a little bit on to get a bit of to intuition what we want to do. We want now to approximate an analytical function. So neural net is, this is really a simple example. What we have is X sampled from 0 and 1, 40 observations. Then T is just like, again, like whatever number pulled off thin air with some noise. Now we split the data. As we are good data scientists, we learn to split the data into various chunks of data. Now we want to run, the approximation, and we do it with really, only 3 neurons, which is really small. But like, notice the critical thing here. We need to do a linear activation function. So we train that thing. And we also invoke early stopping. So you see what it does. The error quickly goes down. Okay, I mean, I didn't run it long, but after 7 iterations, it already stopped. So you see, it's a universal function approximator at the very base. So like, given some noisy data, you can well, approximate functions relatively easy. And let me actually quickly go to the slides. So, before you go tomorrow to the fancy TensorFlow library, what I suggest you to do. So like, I'm not asking you to do any cleaning of data or so, but after we finish our discussion here in relatively short time, what you should do is you should try to extend this analytical function. Right, so this is a famous, so this is like, I believe, Gent's 1984. There's a bunch of test cases to test well, interpolation schemes, so to speak. So what I would strongly suggest you to pick a bunch of those functions. So first in the 2-dimensional setting. So before I made your life easy, you should do a 2-dimensional function, and then you should generate varying trainings, observations. The training set should be increased from the domain 0, 1 to the power of 2. And then what you should do is you should compute the L2 error, and you should play with the architecture. So here you cannot play a lot. So like, you can add more neurons, you can play a little bit with the momentum, so the learning rate, so to speak, and essentially see how the approximation error changes, also like with numbers of epochs, so to speak. So that's I think a good but easy exercise to get a feeling of for neural nets. Now let me go back again here to the actual example. So that's the first thing. So like we trust a multi-layer perceptron only with one hidden layer and very few neurons can approximate this XOR data set. We can approximate functions. So here's a noisy function. Now let's look at the actual iris data set. And by the way, there's a side remark. So I will talk more about it tomorrow. There's from the ISC Irwin. There's like there's a machine learning repository which has really a ton of data sets available. So like if you want to get a bit into the game and you want to fit different models to interesting data, this is a good point to look into. I'll show you in a moment, but let's look at first this data set that we prepared. So as I said, we have these 3 classes of flowers with a label. So let's, we define a function to load it in, blah, 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 blah. Then we split the data. We, we shuffle them, so they come in random order. Now let's run it. And you see, even with the simple architecture, so here we have now 5 neurons. We have logistic, so the output should be between 0 and 1. We have again early stopping. Then if we invoke the confusion matrix, we get the 97% correct prediction of our test data. And again, like you see, this is a kindergarten size neural net, so it's an impressive thing to do. Now, let's move on to the last example of the data that I have prepared for you to look at. So it's this MNEST dataset from Jan LeCun. We need to load it in again. Difference here is, so before we had 3 classes, so here we have 10 classes. We have 10 numbers, we have 10 classes. So this is what we deal with here. We split the data, and again, like we need to have an activation type of some sort. So here we choose just softmax. Now let's run. So this takes a little longer. And so one note, what I do here, I do a loop with the number of neurons, so increase that. So like I train it once with 1, then with 2, with 5, 10, and 20 neurons. So like when you scroll down, you see, the first one is only 21% correct. You have 36% correct. When you increase the size of the network, then you have 62% correct if you increase the network even further, so like the number of nodes. Then you have 71% correct. Then, well, it saturates at some point if you need to go bigger. But you see, mechanically, you need to enter the data. You need to choose, you need to split the data. Then you run it and you hope for the best, and then you see what the error looks like. So in that sense, but like I didn't do a break before. So what I now would strongly suggest to you is the following. So in the next, well, actually the rest of the day, in the next 45 minutes, what I suggest is the following. So you should carefully study, this code here essentially contains everything that I was teaching you this morning. So what you should do is really carefully step through that notebook on your own in the spirit of inverted classroom. Once you did that, you should try to just like do this basic homework, so to speak, and I'll be available, either through Slack, or I mean you can send it in the channel or in a private if you have questions with regard to to the two notebooks here, or to the material in the morning. And as I said, like, so we covered today just a lot of material. And what we do then tomorrow, just like to skip ahead a little bit. So tomorrow we will really do the proper thing, meaning we will look at first TensorFlow, we do basic classification and regression tasks. And then we will look at the more complex, way more complex things by using recurrent neural networks and neural networks in the context of deep Q learning. So that's kind of the logic. So like I strongly suggest to just familiarize with the things that you have learned so far. So is there now immediate, or like not immediate? So is there questions now?
How do you split the data set to training, test, and validation sets? What is the size of each set?
It really depends a bit, but like, so in practice, so often in papers you read like 80-20, so 80%, 80%, 20%, then depending if you have like also, so like if you have training and test, it's like 80-20. If you have validation, it's probably 50-25-25 or 60-20-20. It's kind of a rule of thumb.
Thank you.
And then other thing is also like, I haven't talked about that, but we will see that tomorrow. It's neural nets are extremely data hungry. So like, I haven't put that here, but so as a rule of thumb, again, like for instance, I'm quoting Marsland, 2014, it's like a rule of thumb, it's like you should at least have 10 times more data points than weights in your network to be on the safe side. I mean, it's kind of hard to say, right? But like, I'm just saying, if you have, so the examples that I have presented you here, there may be, there are machine learning techniques which are way more efficient with data. So neural nets are really designed to cope with a lot of data. So like, for instance, if you have few data points, Gaussian process regression may work probably, better given the amount of data if you look at the performance, whatever performance measure. But just saying.
Okay, do we have any other questions? It doesn't seem so.
Yeah, so and again, like I will be on the chat for the next 40 minutes or so, and please go through those things carefully, because like tomorrow there will be more action required. Okay, then like I'll go on mute and switch off the camera. If there is any questions, I'll answer. Otherwise, I'll dial in quickly in like 40 minutes. So good luck with the exercises. See you in a moment. Anybody in here?
Let's ask on Slack.
Sorry? Okay.
Let's ask on Slack.
Yes, 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 indeed, indeed. Yeah. There's few people still around, probably most left for an afternoon coffee. Yeah, so I think people wandered off after the exercise. So let me just briefly before, like we adjourn and meet tomorrow, just wrap up the takeaways of today. So like, as I, threatened you this morning, it was a, theoretical day. So we really covered the fundamentals of deep learning. That means we looked at the perceptron, the multi-layer perceptron, fully connected deep neural networks. We, from an abstractive perspective, looked at activation functions, when you should use them and why you should use them. We learned how to write down cost functions as a means to determine the optimal parameters of the network. And then in the afternoon was a bit more lightweight. So we looked into, in a, I would call baby implementation to showcase how a multi-layer perceptron or a standard neural net looks like. Then we confronted that to real data and to analytical functions, and we let you play a bit with that. So, please, tomorrow we will essentially run codes without thinking too much what is happening underneath. So this is like what I expect from you tomorrow to, somehow be familiar with. Difference being tomorrow, so like in the morning, I will be, gentle in a way. You will have tomorrow way more time to, like to train or play with Jupyter notebooks on Pit Stained. So we will have like more realistic data sets than the stylized today. Other than that, we covered actually quite a bit of material today, so should also have a bit of a rest. The questions that were on Slack seems they were all answered. Is there something right now that you would need or would like to ask?
I don't see any raised hands.
Okay, then I would say have a good rest. Try to digest the material that we covered today, and then tomorrow we do the proper thing on the bigger machine than like the things that you were able to solve right now. Thanks for your attention. and see you tomorrow.
Thank you, Simon. Thanks.
Before we
everyone.
finish, let's give Simon a virtual round of applause.
It's very important.
Thank you.
So we'll have the
Thank
Q&A at 4. Are you available, Simon, at 4 if people join for the Q&A?
Yeah.
Okay. Okay, then.
But it was a different Slack, no? Slack. It was a different Zoom.
Yes. We wrap up now because this is the streaming, and then we have a regular Zoom meeting at 4 where people can join and ask live questions.
Cool. Yes, sure. Okay.
Okay, thanks.
See you then.
So,
Have a good break. Ciao, ciao.
Radim, I think you can close now the meeting.
Okay, bye.
Bye.